Yay. Okay. So we're really going to spend time in this section to look at the domains and ranges because it's going to be really important, especially when we do applications. The whole reason we learn math is to apply math. I mean, math in and of itself is beautiful. It's lovely. It's a happy place for me. But being a recovering engineer without having applications of math, it's not really all that great. So I really like to make those connections between this is the math and this is why you need to know it. So we need to know domains and ranges. So we need to know what we can put in and what's going to come out, especially with applications. We're going to spend a lot of time with the domain and range. And when we talk about the domain, we have to restrict the domain at times, and we have to pull out numbers we can't use. And that's going to force whatever the range happens to be. So the domain is the one that we really pay attention to, and then whatever shakes out is the range. So we want to think about the domain as being our input or our x-axis, but I don't want us to be just stuck on the x-axis because we have the ability to use time instead of x. So we'll use t instead of x, and so our domain would be in terms of t, the time it takes to do some sort of distance or whatever our application is. So our domain is the things we get to put in. It is usually along the x-axis, even if we're labeling it as t. And then the range is along the y-axis, and those are the things that come out. So you want to think about the domain being these are things we're going to do to it, and then the function is a set of rules. So when we're talking about the function, it's just the set of rules that we have to do to that number to get us to the output. So that's all the function really is how do we get from our domain to our range. And so when we're describing sets, in particular, when we are describing our outputs or our inputs, there are three ways to do it. There's four ways to do it. We can just say verbally, this is the set of real numbers. We could use the roster method. Now, we don't typically use the roster method, this one right here, unless we have particular numbers. So we never used the roster method if we are looking at the set of real numbers. So the roster method is only used if we know the exact elements of our domain or our range. If our domain is real numbers, we don't use the roster method. The other way we can do it is a set builder, and we were talking about what the set builder looks like. And then the fourth way right here is interval notation. So we use interval notation when we don't feel like using the roster or the set builder. You can use either one. You're going to see in the homework that it's going to mostly ask you for the interval notation because the way coding is. It's really hard to code the curly brackets and the argument and the such that. So you're going to see most of the coding and most of the homework and on the tests and the quizzes are going to be using interval notation because that's a much easier thing to code. We like to use both. We want you to be fluid in both. So let's take a look at some examples in which we're describing our sets. So here's the verbal example is we have the set of whole numbers less than or equal to 6. So that's how I'd write it out verbally. Now that's a lot of writing, and math people usually are not real happy about writing. The roster method, because I know the exact elements, I know that it is 0, 1, 2, 3, 4, 5, 6. That is the roster method, and I know the exact elements. I use the set builder as I say, okay, here is x such that x is less than or equal to 6, and x is an element of the whole numbers. If I don't write this portion of it right here, then the assumption is I'm in the land of real numbers. So if you are using set builder and you want numbers that are not real numbers, you want whole numbers, or you want integer numbers, then you do have to write which notation you want. So that means we got to be comfortable with what the notation is for whole numbers, integer numbers, and all of the other ones. Before I move on and explain that though, the reason I can't use interval notation on this particular example is that interval notation is set for real numbers. So because I'm not using real numbers, I'm using a particular subset of numbers, they are the whole numbers, then I can't use interval notation on this particular one because it is not all of the numbers in between 0 and 1 and all the numbers in between 1 and 2 and etc. So I can't use interval notation on this particular example because I have a particular set of elements that I know. So I know the number of elements I have and I know what they are. They're not like a real numbers where there's an infinite number of numbers between 0 and 1, so I would use interval notation if I wanted to look at between 0 and 6 that are real numbers. So let's take a look notationally. Is we've got the empty set, and the empty set, I know if you're a computer science major that you really want to use that, and I understand because I've coded before. I did it for a job. I did it for a living for a while. Didn't care for it much, so no. The 0 with a slash through it, when I see it in math, it means the empty set. So if you are making notes to yourself and you're a computer science major, please make that note that when you see 0 with a slash through it, that does not mean 0. I understand with coding you want to make the difference between a 0 and an O, especially a capital O, so I get why you all do that, but in math, when I see that, it means the empty set, not 0. So make sure that you either stop doing that, at least for this class, or you make sure that you want to use the curly brackets that are empty. That's the other way of doing it. And then the third way of saying an empty set, and I'm going to explain what an empty set is in a minute. The third way of doing the empty set is x such that x is not equal to x. And that's the most awkward, I find, way of writing the empty set for me personally. So what the empty set is say we get down to solving an equation, and then I go to check that equation, I check those solutions in the equation, and it doesn't check. Now, I know I did all the math right, and there will be examples when I get further into class, and I did all the work, and I know it's all right, but when I go to check those values, the values make it so that it's not a true statement. And so I have a no solution. There's no solution to this particular equation, and so I would say my solution is the empty set. As an example, when we talk about absolute values, so if I said the absolute value of x, which is less than 0, well, there is no value of x that's going to be when I take the absolute value, which is going to be strictly less than 0, because absolute value means distance to 0. And unless you're in a physics class, all of our distances are positive. So the solution to this would be the empty set. So I'd write it with curly brackets like that. My right-hand curly bracket isn't very nice. Or I do a 0 with a slash through it. So there is no solution to that particular inequality because there's no value that when I take the absolute value of it is going to be a negative number. So this is an example in which I would use the empty set. The natural numbers are the numbers that we first learn, and that is 1, 2, 3 on up. They're the counting numbers. You might hear them as the counting numbers. So the natural numbers start with 1, 2, 3, going all out. Whole numbers start with 0, so we get to include 0. The integers are the -1, -2, -3, 0, 1, 2, 3. It does not include any fractions. It does not include any decimals. It's just the numbers that you would see on the number line, the numbers you actually see on the number line, and not anything in between those numbers. The rational numbers, you'll see them as Q. So you'll see them as Q. They are the numbers that can be wrote as a decimal that repeats or ends, or can be wrote as a fraction. The irrational numbers are the numbers that are not actually, or they're P. See the irrational numbers down here are the numbers such like pi or the square root of 2 or some number that I can't write as a repeating decimal, a truncating decimal, or as a fraction. Real numbers have everything. So the real numbers hold everything, and I'll show you a chart of what all that is. And then the complex numbers is the numbers in which we end up with negatives underneath square roots. And we will get to those later in the quarter. So I'm going to show you how the way that these all kind of start out with. So the natural numbers are the smallest number group. So I'm going to put those in the smallest circle here. So I know I've got a leg, so I'll just kind of wait. So those are the natural numbers. Now, the natural numbers are contained within the whole numbers. So the whole numbers contain the natural numbers. And then the integer numbers contain the whole numbers. So the whole numbers are contained within the natural, or within the integers, which are contained within the whole numbers, which are contained within the natural numbers. My next group out are my integer, or my rationals. So every one of my integers are contained within the set of rationals. My whole numbers are contained within there. My natural numbers are contained in there. We call those subsets. So the bigger circle is the set. The smaller circles within are the subsets. And then we have the P, which are the irrational numbers. The irrational numbers is the bigger set. The Q is contained within there, so it's a subset. And then from there we have the real numbers. This contains everything else. And then my largest one, which I'm running out of space here, I'm just going to go like this, is my complex numbers. So my complex numbers is the largest number set that we have. And every time I go in, I got to be careful, because I can't say a complex number is a real number. And a real number isn't necessarily, well, a real number will be the irrational, but an irrational is not a rational, which means that the rational number may not be an integer, and etc. So going that way may or may not be true, but coming out is always true. So this is always true, and coming inwards may not be true. So what I mean by that is I can write a complex number as, it's supposed to be a plus bi. If b is equal to 0, then I could write this as, like, say 3 plus 0i. This is a complex number, so it lands here, 3 plus 0i. The 3 part is real, it's irrational, it's rational, it's an integer, it's a whole number, and it is a natural number. So that 3 will go all the way in. But if I would have said pi, so I'll do this in green. So if I say pi, so I do pi plus 0i, so pi plus 0i. It is a rational, or it is a real number. The pi part is, because I have 0i. It's an irrational number, and that's as far as I can go with that number. It's not going to go any further. It's not an irrational. It's no further. I have to stop at that ring. But if I have, say, the number 7, 7 is going to be here, 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 and then 7 plus 0i. So the 7 will always come out, but coming back in or out depends on what kind of number you have. So I'm going to stop and drink some coffee, and I'm going to let you ask me any kind of questions you may have. You can raise your hand, or you can just put that in there. Yes, so the question is, can, since the natural numbers are endless, but they're not as large of a group as the next grouping out. So when we talk about infinity, yes, there are different sets. We call that cardinality of infinity. So the real number infinity is a larger number than the natural number infinity, or even just one ring in. So the bigger the ring, the larger the infinity is. So yes, it is actually, we can talk about largeness of infinity now. Yeah, if you go into math, there is times where, like, I think I've gone into a different dimension. I don't know what the hell is going on right now. Anyone else? Okay, cool. So Then we want to look at the interval notation, set builder notation, and roster. Most of the time we're going to be in the land of real numbers, so most of the time we are going to be using the roster, or not roster, I'm going to be using the interval or set builder notation. And if I'm in the set builder notation, if I don't tell you where the number belongs, like the previous example in which I said, hey, this comes from the whole numbers, then it is by default real numbers. So as we take a look at this, here's what the inequality would look like. So inequality is x is greater than a. So the interval would be from a non-inclusive to infinity. The description is x is greater than a. Now I'm going to write underneath it what the set builder notation would look like. So the set builder notation would look like this, with x such that x is greater than a. So that's what the set builder notation would look like for that. The next one is the x is less than. So the set builder would be x such that x is less than a. And again, we are assuming we're in the land of real numbers. Now notice that here we use parentheses and parentheses because this is non-inclusive. We use parentheses and parentheses because a is non-inclusive. Now when we go to the next one, we have the equality. So we have x such that x is greater than or equal to a. And because we have the greater than, we have a bracket and we have a bracket. So we put a bracket both on the interval and we put a bracket on the number line. When we look at our next one, we have the less than. So x such that x is less than or equal to a. And again, you're going to see the bracket and the bracket, because we get to include a, whereas the previous two we weren't able to include a. So the set builder is x such that a is less than x, which is less than b. And notice how each time I'm doing set builder, it's pretty much just taking that inequality and just rewriting it with the curly bracket x such that. So if we are using the inequality, so we're using the inequality for solving, then sometimes it may be easier to use the set builder. But if you are loving interval, by all means, please use the interval notation. There's really no reason to use one over the other than the fact, like I said, for coding purposes. So if we take a look at our next one, again, x such that a is less than or equal to x, which is less than b. And we have a bracket and a parenthesis, because based on whether or not it is inclusive or not. And moving to the last couple examples, x such that a is less than x, which is less than b, and x such that a is less than or equal to x, which is less than or equal to b. Okay, so I am going to stop there, give you a moment to contemplating the kind of questions you may have for me, and I'm going to have a drink of coffee. So moving on is now we're going to start looking at finding the domain. We're going to look at the domain from algebraic standpoint, and we're also going to look at it from the graph or from a chart. So we've got to be able to read and write the domain based on what's given to us. So what we want to do is we want to look at right now in this class, we want to look at, we're looking for two things in particular. Is I want to see whether or not there's an x in the denominator and I'm going to be divided by 0. So that's a problem. So I'm going to look for x in the denominator. And then I'm going to make sure that I don't have any non-real numbers. So I'm going to look for square roots. Square roots, 4 through 6 roots. I don't care about cube roots. Cube roots are okay. It is the square roots, the square roots, the fourth roots. Anytime the index, and when I'm talking about index, see I see the nth root here. That number there is called the index. And if I'm talking math speak and you're like, I have no idea what she just said, please raise your hand, ask the questions. I don't mind answering the questions. I don't know what you don't know, so if I'm talking about, the index or whatever, you need to ask me. Now I know that this is one of those things you've all learned and forgot, so I'm refreshing it right now. but there are going to be times I'm going to forget. So please, please, please ask the questions. So anyways, going back to what I was doing is that I'm really looking for at this point, is x in the denominator? Is there a fraction in there where x is in the denominator? Or is there a square root, fourth root, or sixth root? Those are the two things I'm really looking for, because those are going to be restrictions. So there's going to be telling me there's going to be values in which I can't have for x. And then I'm going to worry about the range later, but most I'm going to be focusing on the domain. So here we go. I'm just going to start with these examples, A through D. Not the graph is not included in D. That's a different example. So which one, A through D, would you like me to do? C? D? Anyone else? D? D? So I'm guessing D. Okay, so I'm going to go ahead and do D. I'm going to zoom in on D so I can really look at it. And when I'm looking at D, I have square roots, so that's kind of a problem. So I'm going to take and address each piece of it. So I'm going to first deal with the numerator. So the numerator says I have a square root. Okay, cool. So I take whatever is underneath the square root. That's the x minus 4. So I'm going to take x minus 4. And I have to ensure that's a real number. And the way I ensure that's a real number is I set it greater than or equal to 0. Whenever I see a square root, that's the first thing I'm going to do is I'm going to set whatever's underneath the square root or the fourth root or the sixth root. I'm going to set it greater than or equal to 0, and I solve. So I solve by adding 4 to both sides, so x is greater than or equal to 4. So as long as I use a number that is greater than or equal to 4, then I'm good in the numerator. So now I'm going to do the denominator. And I have x minus 6. Do the same thing. I have to ensure that x minus 6 is at least a positive number. Now, this one's going to be slightly different because not only do I have to ensure it's a positive number, but I also have to ensure that it's not 0. And that's only because it's in the denominator. It's in the denominator, so I don't get equality on this one like I would have done on the one in the numerator. I can have 0, I can divide into 0, but I can't divide by 0. And that's how come right here I don't have the equality. But I'm still going to do the same kind of thing as I'm going to go ahead and solve for x. So I'm going to add 6 to both sides. And x has to be strictly greater than 6. Now I'm going to decide which one is going to dominate. Well, the one that's going to dominate is the denominator because first of all, it's a larger number than 4. So I can't put anything less than 6 into the denominator. I can put numbers that are greater than 4 in the numerator and not have a problem, but I can't put anything less than 6 in the denominator. I could put 6 in the numerator and we're cool, but I can't put 6 in the denominator because I'd be dividing by 0. So this, it's really going to dominate which one I'm going to use for the domain restriction. So the domain restriction is x such that x is greater than 6. So x such that x is greater than 6. Or interval notation is a rounded parenthesis 6 to infinity. I'm going to stop and ask if anyone has any questions. All right, so go ahead and do A, B, and C. Oh, so the question is, we just want the domain. Yeah, we're not going to rationalize it or anything. We're just saying, hey, what are the values I get to have? And the values I get to have on this particular example is x has to be greater than 6. So that is the only thing we care about at this point. We just want to know what the domains are. We'll worry about ranges if we have graphs or when we get further into the graphing part of it. But right now we just want to know what the domain is. Any other questions? Okay, so please do A, B, and C. And we probably won't have time to finish this because we only have about 2 minutes, but I do want you to get started on A and B. And then we'll talk about these. We'll pick these up again tomorrow at this place.